Today we'll be continuing looking at derivatives of exponential functions, but instead of looking at y equals e to the power of x, we're going to look at when we have a base of b, so y equals b to the power of x. So let's recall from yesterday, if f at x equals e to the power of x, f prime of x is equal to e to the power of x. And if f at x equals e to the power of gx, then f prime of x is equal to e to the power of g of x times the derivative of g of x, so g prime of x. But these rules only work with a base of e. So let's look at finding the derivative of y equals b to the power of x for b not equal to e. So let's first recall a couple of log rules. So recall here that 2 log base 2 of x is actually just equal to x. And a to the power of log a to the power of x is equal to x. So you notice anytime you have your base and to log to the base of a here, so anytime those are the same, your function will just equal to x. So, therefore, e log base e, p is equal to p, just following those rules. However, since log e x is equal to ln of x, then we have if f at x is equal to b to the power of x, and if f at x were to be equal to e ln b to the power of x, then f at x would be equal to e x ln b. And f prime of x is going to be equal to e to the power of x ln b, so this follows from yesterday, times, now we take the derivative of the exponent, 1 ln b plus 0 times x, because ln b is just a constant. So this will be equal to e x ln b times ln b. So therefore, f prime of x is equal to b to the power of x times ln b, since b to the power of x is equal to e to the power of x ln b. So in summary here, for f at x equals b to the power of x, f prime of x is equal to b to the power of x ln b. But we don't always have f at x equals b to the power of x. You could have f at x is equal to b to the power of g of x. So when that happens, you're going to let u be equal to g of x, and you're going to use the chain rule on fu equals b to the power of u. So therefore, for f at x equals b to the power of g of x, f prime of x will equal to b to the power of g of x ln b times g prime of x. So the best way to really understand how to take the derivative of an exponential function in the form y equals b to the power of x is to actually do some examples. So our first example here is f at x equals 2 to the power of x. So our b here is 2, and then our exponent is x. So by our rule, f prime of x is equal to 2 to the power of x times ln 2. And that's all we need to do. Our next one, we have f at x is equal to 10 to the power of 3x squared minus 4. So we do the same thing where we take, we leave our 10 to the power of 3x squared minus 4. Then we take ln of the base, which is 10. Then we take the derivative of the exponent. So that's our g of x, which is 6x. And that's as far as we can go in that question. C, we have f at x equals 2 to the power of x times e to the power of x. So here we have two terms we're working with, and therefore we will be using our product rule when defining the derivative. So f prime of x will be equal to 2 to the power of x ln 2 e to the power of x plus 2 to the power of x. Now the derivative of e of x, remember from yesterday's note, is just e to the power of x. So notice here I can factor out a 2 to the power of x, e to the power of x, and I'm left with ln 2 plus 1. Remember, that's just simple factoring. Our next one, we have f at x is equal to 6 to the power of x squared all over e to the power of 2x. So here we are going to take the derivative and we're going to use our quotient rule. So first we're going to derive our 6 to the power of x squared. So we have 6 to the power of x squared times ln 6 times 2x e to the power of 2x minus, we have our 6x squared. Now we're going to derive our e to the power of 2x. So that's times e to the power of 2x. And then we have to derive the exponent here, so it's just times 2. All over, we need to square the bottom, so we have e to the power of 2x all squared. So now let's factor out anything we can in our numerator. So in our numerator, I can factor out a 2. I can also factor out a 6x squared. And I can also factor out an e to the power of 2x. And when I do that, I'm left with x ln 6 minus 1 all over e to the power of 2x squared. Now, what you're going to notice here is everything is multiplied together in my numerator. I have 1 e to the power of 2x in my numerator, and I have 2 e to the power of 2x in my denominator. So I can take 1 away in my denominator and take the whole thing away in my numerator. So what I'll be left with is 2 6 to the power of x squared times x ln 6 minus 1 all over e to the power of 2x. Now in our second example, we want to determine the equation of the tangent to y equals 10 to the power of x at the point 110. So our first step always is going to take the derivative. So the derivative of our function is equal to 10 to the power of x ln 10. Now since I know that this equation is had determined the equation at this point, 110, I'm going to sub in 1 there for my x value. So this will tell me the slope at this point. So we have 10 to the power of 1 times ln 10, which will just be equal to 10 to the power of ln 10. So our second step, I know my slope, which is 10 to the power of ln 10, not to the power, sorry, 10 times ln 10. We have our x value, which is 1, and we have our y value, which is 10. And that just comes from giving us our point in the question. Now our third step, I know my formula for any tangent is y equals mx plus b because it's just a linear line. So now I'm going to sub in for all my known values. So I have 10 equals 10 ln 10, which is my slope, times 1 plus b. So I can isolate, so I can solve for b. So 10 minus 10 ln 10 will be equal to b. Now I can put this into my equation, y equals 10 ln 10x plus 10 minus 10 ln 10. And now if we want this here, right, is our exact form, but if we were to want to graph this, we need to actually know what ln 10 times 10 is, and so on. So y equals 23.03x minus 1303. Again, just use your calculators to sub in for ln 10 and multiply those things together. Now, our last example here. On January 1st, 1805, the population of Gold Rush Town was 50,000. The size of the population since then can be modeled by the function p of t equals 50,000 times 0.98 to the power of t, where t is the number of years since January 1st, 1805. So that's important to remember the date. What was the population in Gold Rush Town on January 1st, 1990? So, what is the difference between years here? So what is our t? How many years has gone by? So in A here, t is equal to 50. And that can be found just by minusing our 1900 minus our 1850. So we're going to sub that value in for our t in our equation. So we have 50,000 times 0.98 to the power of 50. And when we do our calculations, we get approximately 18,208. So therefore, the population was 18,208 in 1900. Now in part B, at what rate was the population of Gold Rush Town changing on January 1st, 1990? Was it increasing or decreasing at this time? So I can see just by in question A here, or part A, that it is decreasing. We went from 50,000 of our population to 18,208. So it is decreasing. We know that. But by how much? So to find that, what we're going to do is we're going to take the derivative of our function. So when we do that, we have 50,000. 50,000 is just a constant, right? Times our 0.98t times ln 0.98. So that comes from your exponential function and taking the derivative of it. So when I calculate that, I'm going to get negative 1010.135 times 0.98 to the power of t. T is equal to 50, so we need to find what the derivative is at 50. So we sub in 50 for our t value. And what we're going to get is approximately 368. So therefore, it's decreasing by 368 people.